Chemistry time. Today we shall talk about, in brown, ionic and metallic bonding. A way that I very frequently begin these videos is by doing what? What are we probably going to do up here first? You've learned this from watching these, even if you weren't actively paying attention. Yeah, let's define what does it mean to be an ionic bond? Likewise, what does it mean to be a metallic bond?
An ionic bond is an electrostatic force that...
I will not accept an answer straight from the book. Let's talk about it as real human beings who really know this.
It's force.
Mm-hmm. Okay, hold up. A force. Well, and how do you know it's a force? What does a force do in physics or in physical science?
Because when your hands touch together, it's a force keeping them apart.
Okay.
Because if they came together...
That's an example. Yes, and I like that example. Why must it be a force? What does a force do in physics?
It helps.
Not always. Forces can cause a change in motion, or position, yeah, either. A change in, because remember, a change in motion is acceleration, and acceleration is defined as the change in velocity over time, and velocity is defined as a change in position over time. And so a force is the driving, well, I was going to say force. A force is the driving impetus, the driving factor, yeah, you could say that, of change in motion. And why would that be relevant to atoms? I mean, it seems like that's removed from what we're currently talking about.
Force holds them together and what keeps them apart.
Okay. A force can hold, when you say them, you mean...
Holds an ionic compound.
Okay, it holds the atoms, or really ions, within an ionic compound together, or...
Apart.
Yeah, or forces them apart. So a force, in this case, what force of the universe is this?
Strong. Nuclear force. Weak nuclear. Strong nuclear.
We're going to run out of them. We already covered half of them, yeah. Electromagnetic. Thank you for not saying gravity, at least. Electromagnetic. It's the electromagnetic force. Holding ions together. How must the ions be to be held together by the electromagnetic force?
They must be in a shape.
Something and something. What must the electromagnetic charges of these ions be in order to be held together by the electromagnetic force?
Similar.
That's the opposite of the truth. Opposite. So it must be a positive and a negative. It has to be. For the ionic bond to form, it has to be a positive ion and a negative ion. Why must it be those?
Because it's like the north and south poles on a magnet.
Yeah. The opposites attract. The opposites in the electromagnetic force attract. And why could it not be some third thing? Why does it have to be positive and negative and not some... Well, I can't give examples because there aren't any, and that's the answer, too. There are no other charges. There are only positive and negative. There are degrees of positive and negative, but there are no other charges. Neutral, I guess, but that's not a charge by definition. So it's the force holding together a positive and a negative ions. And these have names. What's the name of a positive ion? Remember?
Positive ion, NH.
That's beautiful. I love that. I can tell you read it. Just like when we see in a book this word, how do you say that? You've seen these TikToks probably where the girl says, I'm going to show you some words that you have read, and you're going to say them out loud, and then you're wrong about it. I'm not, because I know everything. But you're wrong about all of them. How do you pronounce this? This is facade. Facade. Bless you. There are others too. But the reason I love that you said that, Tiana, is because I can tell you read it and you understood what it means. You just don't know how to pronounce the word. This word, you could think that, but it's actually pronounced cation. Cation. Cation.
I thought it was caution.
I know, that's why I think it's good, because even though you're mispronouncing it, which is by its definition wrong, it's good. It tells me that you read it and you understand it. You just don't know how to pronounce the word, and that's okay. And then what might we call a negative anion? Anion. The way I remember these, do you remember the way do you remember something about me that lives in my head? The way I remember these from physical science? The answer is no. I remember that a cation, a little tiny cute kitty cat, is a positive thing. Look how happy he is. I hate cats in reality. That's why this mnemonic works for me. The cation is a happy little positive thing. Look how happy he is. And here I'm using positive in a way that the universe does not deign. That is to say, the universe doesn't say positive means good. That's a human characteristic that we apply to things. Like if I say, you've made a really positive change in your behavior this year, young man, I would mean a good change, but that doesn't necessarily mean good. But it's a way to remember it. And then I remember the other one as onion. Stinky, stinky, bad onion. Bad, negative. In reality, I like onions. I really do like onions, but you can remember it as stinky, stinky, negative onion. Nice, positive, happy kitty cat. Cation, anion. You can remember that way. You can remember it however you want. I'm not telling you how to live your life. I'm just saying this is a way you can remember it. Let's say what a metallic bond is.
The opposite of ionic.
No.
Let me look at my definition.
I have a question.
That's it.
Is it more nuanced than this? I mean, is this true fundamentally? Yes. Is this the end-all, be-all of the truth? No. No, it does get more complicated than this. It gets more nuanced. There are degrees of charge, for instance, and we're talking about how we can relate an amount of negative charge to a different amount of positive charges. But for the most part, this is true, at least on a basic level. And what about a metallic bond? Well, let's start it the same way. What must a metallic bond be? What are all chemical bonds? It's a force. Force. Let's skip what fundamental force it is for now and just say what it does. So in the way that the ionic bond held ions together, and I rewrote the word ions here like a schizophrenic. No, don't make fun of people with mental illnesses. It's not fun. A force, in the same way this one held ions together, what's this one going to do? Yeah, hold
Metallic
atoms of metals together. Let's be very specific about this word atoms. What does this mean? Because we have a kind of a loose definition that we use from the time that we first learned the word atom. And what do we mean specifically here? What must this mean in chemistry? No? Do you remember? Yeah, they have to have the same number of protons and electrons. So this means that it's an uncharged, I'm going to put in quotes here, atom. Because remember, we use the word, when we're speaking strictly, we use the word atom to only mean an uncharged atom again. But why would this be? What if it did have a charge? Could it still be part of a metallic bond? I mean, it does. That does happen. That's how electricity works. But if we were noticing that on the large scale, then it would instead be an ionic bond, because this is by definition those of charges. That doesn't mean that this can't hold a charge. In fact, that's one of the benefits of a metallic bond and throughout a metal is that it will transfer a charge. But on average, it remains itself uncharged.
So it says the attraction of metallic cation and delocalized electrons.
Yeah. Let's diagram both of these. This is also going to talk about how they form. What do we need to have an ionic bond, according to our definition? What things must be present for us to have an ionic bond?
Two opposite ions.
Yeah, a cation and an anion, two opposite ions. And let's get more specific, and let's say that in this case we have a sodium and we have a chlorine. And what element or what substance is this going to make when we form it? Sodium chloride, which we call table salt. But let's diagram this. Here we have a nucleus, and we'll just draw a nucleus because we're not really at this point worried. We could diagram, we could specify that this is sodium 23 and then it has 11 protons and 12 neutrons. We could do that, but that doesn't really matter for the chemistry of it, because what subatomic particle does matter for the chemistry? Yeah, which is to say electrons. The electrons, and specifically which electrons? The valence electron. So we're really not worried about what's in the nucleus, so I'm just going to represent a nucleus here. And the same way with chlorine, we're going to represent it with a nucleus. I'm going to draw a Bohr model. Why would I do that? We know that's not how they actually work. Why would I ever bother drawing a Bohr model when I know that the quantum mechanical model said that these electrons are actually waves? And I should be drawing a waveform of different shapes and sizes. Why would I do the Bohr model instead?
How they work around, how the valence electrons work around the nucleus.
Yeah, you're all kind of coincidentally orbiting the truth. But I'm just going to draw them as orbits because it's easier. It's a model. It's going to give us the information we need about how many electrons it has without having to get into in-depth about their specific configuration. Because just like we're not worried about what's in the nucleus for this particular case, we're not really worried about the waveform of the electrons or the shape of the orbitals in this particular case. We understand those things exist, but the model is a simplified version, helping us understand what we're really getting at here, which is the bonding. And we don't need any of that for the bonding. So I'm going to draw a Bohr model. How many electrons should I put in the first energy level? 2. Why only 2? But Rhett, isn't it that sodium has 11 electrons? Why would I only put 2 in the first energy level? That's the rule. That's the rule. 1s2. That's all that can fit in energy level 1. Oops, that didn't really work. Just gonna put it outside.
2s2, which is 4.
There's 2s2, but then there's also
3p6.
Try again.
3s2.
No, stop. Just saying things, please. There's 2s2, so there's also 2p6. 1, 2, 3, 4, 5, 6. I tried to draw. I'm going to draw these actually this first energy level within it, so that kind of makes a little bit more sense. I would, if I was taking even a little bit more time, I'd probably draw these, and you can do this in your notes. I'd draw them in circles, kind of orbiting in the orbit. That would be better than just drawing them floating in between. And then lastly, what?
Well, if there's
3.
That's all that you're paying.
Say the rest of it. Yeah, 3. I want its electron configuration. We have 1s2, 2s2, 2p6. Now we have
3p10, 3s2,
sodium.
3p6. Sodium.
3s1. There's one little valence electron hanging out over here.
But I thought there was 3 valence electrons.
1s2, 2s2, 2p6, 3s1.
Oh.
Do we have to do the electron configuration to figure out how many valence electrons it has? No. What's the easier way to figure out how many valence electrons it has? It's just in group 1. Let's do chlorine now. I'm going to do chlorine a little bit over, and I'm going to do it in a different color, I decided.
Chlorine has 7 valence electrons.
Okay, we have the nucleus.
The last one is D.
What should the first one be?
1s2.
1s2. Next.
2s2. 6.
Okay. Next.
3s2.
Oh, I drew 3. Sorry, 3s2. And then 3.
5.
Sorry, say again.
We're at
I did 3s2. I accidentally drew too many electrons, but 3s2 now.
3d5. 3p5.
He says 3d5, you say 3p5, and she says 3p6, and I don't know what order that was. Which of those is right? One of them is right. This is multiple choice.
Or 3P5.
He said the same thing. You now said 2 different things. Let's all agree on which. No.
Oh, it's p5.
However many are left.
Now you say p5. You say p5. She's nodding p5. Do we all agree it's 3p5? 1, 2, 3, 4, 5. How many valence electrons total? You're right. It is 7. Let's try to think before we give an answer. 1s2, 2s2, 2p6, 3s2, 3p5. How many valence electrons? 7. 7 valence electrons. How many valence electrons in the sodium? 1 valence electron. Are these ions? No, they're not ions. These are atoms. How do I know?
Because they're balanced.
Yeah, they have the same number of protons as they do electrons. I would hesitate to say balance. You could. I mean, that's not wrong. It's just that we use balance specifically to mean balancing chemical equations. Usually, I would say that they're neutral. They're atoms. They're neutral atoms. They have the same number of protons and electrons. So is this an ionic bond? No. Now, what is? There's a missing link here between this 2 atoms of sodium and chlorine and an ionic bond. What is it? How many? Not want. I'm going to say want, but I don't mean that, and you know that I don't mean that. I don't mean they're sitting on their couch watching Netflix and thinking, oh, I really want Burger King chicken fries. They don't want anything. But the universe tells them that they are more stable with 8 valence electrons. So don't forget this key component here, which is the octet rule, which you remember from last time. And the octet rule says that sodium would be better off if it did what? And by better off, I don't mean in the same way that you would be better off if you get away from your cheating boyfriend. If it removes one electron from itself. And how can it do that? And I love this example. I use this all the time. Apparently it doesn't resonate with people because I ask them later and they forget. But in the same way that your parents want you out of the house. They're sick of you. You're a teenager. They want you gone. But they can't just kick you out. They're not going to just drive you to Saturn and drop you off somewhere and then come home without you. In the same way that they can't just leave you, get rid of you, and have you go nowhere. The sodium can't just get rid of an electron. It can't just be like, see ya, off into the ether of space. Your parents have to wait until you go to college, or until you go work at Arby's, or until you go work on a ranch. They have to let you go somewhere else. You have to have a place to go. They can't just vanish you.
So if you left one atom, you went to another atom.
So where this little electron is rejected by the sodium, metaphorically,
Then it goes to the chlorine.
and the chlorine wants one more. So now, ew, how did the hair get on my whiteboard? That's never happened. The octet rule, orange, says that the sodium will lose an electron, and with it, this entire 3s orbital. Now it's at 1s2, 2s2, 2p6. How many valence electrons does it now have? 8. The chlorine now, 1s2, 2s2, 2p6, 3s2, 3p6. How many valence electrons does it have? 8. They're both satisfied with the octet rule. They're both more stable now because they have they bonded yet, really? No. The sodium has given an electron, becoming sodium ion, cation specifically, and the chlorine has has gained an electron, becoming an anion, the chloride anion specifically. And now, this is where the bonding actually occurs, and I'm going to do this. And what kind of bonding is this? I'm going to do it not in blue. I'm going to do it in green. No, try again. This is an ionic bond. And whence cometh the ionic bond? That is, where does the ionic bond come from? It is the force holding ions together of opposite charges. So now that the sodium is a positive charge and the chlorine is a negative charge, they are attracted to each other through the electromagnetic force. In the same way as Payton said that the north and south pole of a magnet are attracted to each other through the electromagnetic force. So what actually holds them together? Their difference in charge. Their difference in charge is holding them together. Now, instead of writing sodium plus and chlorine minus, we write NaCl. And what do we call this? Well, let's name it. To name an ionic compound, we write the name of the cation, and then we write the name of the anion, but change the ending to "ide." That is, we write the name of the anion, which is the same as the name of the original element, but changing the ending to "ide." And I chose sodium chloride because you've already heard of sodium chloride. I also think that this all will be reviewed. Once you get the worksheet for naming and you understand how to do it, like once you are refreshed in your memory, since you've all done it before, you'll fly through it. It's going to be really easy for you.
Can you model this with
Would there
electrons?
be a sodium chloride?
Yeah, there could be sodium chloride. I'm not sure that it exists, but sodium, let's talk about chlorate, because we do have polyatomic ions in here. I'm glad you asked that question. Let's talk about chlorate.
Means it would be
Wouldn't there be 3?
anion.
Hold on a second. Let's. You still need this up here.
No.
Okay. Let's erase this one, and let's talk about polyatomic ions real quick. Both of these were, if polyatomic ions are those ions what contain polyatoms, poly meaning more than one, many.
But a polyatomic ion.
Wait, let me finish. I was in the literal middle of the question. A polyatomic ion, if polyatomic ions are those ions that contain many atoms, what would each of these have been called? Sodium and chloride are
5.
poly many. What would we use for, how many are they?
2.
No, just this one. 1. So we call that, instead of a polyatomic ion, we would call it a
Atomic ion.
monatomic ion. 1, monatomic. It was the compound. I see where your confusion is, and I should have probably phrased it different. The compound was a binary compound. 2 things, sodium, chloride. Sodium, chloride. But each one of those, sodium, chloride, are monatomic. They have just one atom. Whereas a polyatomic ion would have more than one. Chlorate, you had said. What's the formula for chlorate?
Chlorate, Cl, O2, wait, chlorate, ClO3 minus 2, 1, sorry. I had to think. Actually, I was just working out an answer because I wanted to.
But that's not,
It's not
you
what
don't,
you do.
yeah, no, that's like, we'll talk about that later. So we have in the middle, or something like in the middle, we have a chlorine atom. I'm just going to draw it like that. And we have around it 3 oxygen atoms. How are these bonded together? Does anyone know? I'll give you a ramrock if you know this, because you should remember from physical science, but we haven't actually talked about it yet.
They are bonded together.
Yeah, what is the bond between these?
Is it a force?
Yeah. I'm trying to decide why both of you get a ramrock or if neither of you get a ramrock. And I'll make my decision as I talk some more. But this whole thing is one ion. The whole thing has a negative charge. This whole lump has a negative charge. These are individually covalently bonded. The chlorine is covalently bonded to 3 oxygens, but the whole thing has a negative charge as a group. Okay? And now we have, once again, our sodium. We'll call it a sodium ion because it has given one of its electrons to this chlorate ion. And now they're bonded together. NaClO3. And what do we name this?
Sodium chlorate.
Sodium chlorate. Which may or may not actually exist. I really don't know.
Minus or no?
Nope. Payne brings up a good point. Why do I not write sodium plus chlorate minus?
Because it cancels out.
Yeah, because they've bonded together. They're now, this whole thing does not have a charge. We think of this now as one thing. This substance does not have a charge.
So it is.
Whereas this is a substance also. That's a little bit of a chaotic way to phrase this. But this is a substance, but it does have a charge, so we still leave the charge on it. That's a polyatomic ion.
So did that become a polyatomic unit?
What? Did what become it? This? No, this is still a binary compound. This is still a, I don't mean that. This is now not a binary compound, a polyatomic compound. There's another word for that. Maybe there isn't. Yeah, this is an oxyanion, which is that it has oxygen in it. No, it's not a binary compound. I don't know if there's a word for ionic compounds that are not an ionic compound. Let's move on anyway. Some of the main things that I want to talk about, we'll do this after the video, but I want to give you a chance to work on a worksheet that will help you with the naming, because that's the main action item that we do on the test. So the multiple choice will be about what we're talking about now. The short answer will most likely be about what we're talking about now, and then you'll have a whole page of naming, and that's what we really want to spend some time on, because that's the thing that needs practice. The rest, this stuff, and I'd hope I'm not exaggerating your intelligence or my teaching ability when I say that you really should be able to get this stuff at face value. Like when I say this is what a metallic bond is, it should just make sense. You should be able to store that up in your brain and write it down on the test later. But with the naming, you already have done some practice because of physical science, but you just need more practice to be able to do those consistently and accurately. Yes?
So this is just an example. If you have magnesium and sulfur and you wanted to make and you put them together to make a polyatomic,
You can't.
Would it be you can't?
I don't know. I shouldn't say you
magnesium
can't.
sulfide?
Yeah, but that's not a polyatomic ion. That's just a compound. Let's talk about that one. Let's actually do that exact example. Let's actually talk about metallic bonding first. Metallic bonding is a little bit different in that we have in a lump of metal, like a penny or the chair leg or wrench, doesn't even matter. In a lump of metal, we have a lattice work of atomic nuclei, specifically metallic nuclei. It's a crystal lattice of atomic nuclei. All of these are nuclei, so they all have a positive charge.
Is this an electron seed?
Yeah. This is obviously not to scale. This is obviously not supposed to be an accurate rendition. I'm just trying to illustrate the model to you. And then the electrons that would have been, for instance, if this is iron, this one should have how many electrons?
26.
26. if this is a lump of iron, and every one of these nuclei has 26 protons and some number of neutrons, each one should have 26 electrons. But instead of the 26 electrons hanging out here, this one's, I don't know how you would even describe this, but maybe the one that this atom came into creation with, the electrons that it first absorbed, are now, instead of just localized around this one iron atom, they're delocalized. So the atoms, the ions, I'm saying the wrong word twice, the electrons that started out with this iron are now delocalized. They're shared and shared alike among all of the irons. It still averages out. For every one nucleus, we still have 26 electrons. The whole thing is uncharged, unless we're putting a charge through it, but it's delocalized. These electrons are not with any specific delocalized electrons. This gives metals their special properties. Remember, electricity is the flow of electrons. So a current applied to this end of the metal will flow through this end because the electrons can move. Nice. Electrical conductivity. It also allows heat to transfer easily. Thermal conductivity. It also allows it to be malleable and ductile. All the properties of metals are because of this arrangement. Before you go, let me give you your worksheet. You have questions about the things we talked about in the discussion, though.